Observability Unlocked, Mastering Prometheus and Grafana for Robust Monitoring. Chapter 1, Monitoring Fundamentals and the Cloud-Native Landscape. In the rapidly evolving landscape of modern software and infrastructure, simply knowing if a server is on is no longer enough. The intricate web of microservices, containers, and cloud environments demands a far more nuanced understanding of system behavior. This shift has propelled us from traditional monitoring to the more encompassing concept of observability. The evolution of monitoring. For decades, system administrators and developers relied on basic monitoring tools. Early approaches involved simple ping checks to confirm network connectivity or script-based checks to ensure a service was running. As systems grew more complex, we started gathering more detailed metrics: CPU usage, memory utilization, disk space, and network throughput. Tools evolved to collect this data, present it on graphs, and trigger alerts when predefined thresholds were crossed. This was effective for monolithic applications running on a handful of dedicated servers. However, the advent of cloud computing, virtual machines, and especially the paradigm shift towards microservices and container orchestration, like Kubernetes, introduced unprecedented complexity. Applications no longer resided on a single, long-lived server. They were distributed across ephemeral containers, scaling up and down dynamically. In this environment, an application might involve dozens or hundreds of independent services communicating over a network. A traditional "is the server up" check became almost meaningless if a critical backend service within a container was silently failing. This complexity demanded a new approach. The focus shifted from merely knowing if something was broken to understanding why it was broken, even for issues that had never been encountered before. This is the core distinction between monitoring and observability. Monitoring versus observability, a crucial distinction. Think of it like being a doctor. Monitoring is akin to a doctor checking your vital signs: heart rate, blood pressure, temperature. They are predefined measurements that tell the doctor if something known is wrong. If your temperature is too high, it's a known problem. Monitoring helps you answer, are we broken? Or are we meeting a predefined threshold? It tells you about known unknowns. Observability, on the other hand, is the ability to understand the internal state of a system merely by examining its external outputs. It's like the doctor being able to diagnose a highly unusual or novel disease, not just by looking at vital signs, but by combining observations from various tests, patient history, and an in-depth knowledge of biology. Observability helps you answer, why are we broken? And what's happening inside the system that I didn't anticipate? It equips you to handle unknown unknowns. To achieve observability, modern systems typically rely on three pillars: metrics, logs, and traces. Metrics. These are numerical measurements collected over time. They are inherently aggregatable and efficient for storage and querying. Examples include the number of HTTP requests per second, CPU utilization as a percentage, or the current number of active users. Metrics are excellent for identifying trends, tracking performance, and triggering alerts when thresholds are breached. They provide a high-level overview or an aggregated view of system health. Analogy: your heart rate or body temperature readings over an hour. Logs. These are discrete, immutable event records generated by applications or systems. Each log entry is a line of text that describes something that happened at a specific point in time. A user logged in, an error occurred, a transaction failed. Logs are invaluable for detailed debugging of specific incidents, providing rich contextual information that metrics might miss. Analogy: a detailed doctor's note for a specific patient visit, detailing symptoms, findings, and treatments. Traces, also known as distributed traces, these capture the end-to-end journey of a single request or transaction as it propagates through multiple services in a distributed system. A trace typically consists of multiple spans, where each span represents an operation, e.g., a call to a database, a microservice communication. Traces help you visualize request flow, identify latency bottlenecks across service boundaries, and understand the dependencies within complex architectures. Analogy: following a single patient's entire journey through a hospital, from check-in to discharge, noting every department they visited and every procedure they underwent. While all three pillars are crucial for comprehensive observability, metrics are often the first line of defense. They are what you typically graph on dashboards and what you use to trigger automated alerts when something goes amiss. This book will focus primarily on metrics, using Prometheus for collection and Grafana for visualization. Understanding metrics, Prometheus types. Prometheus, as a dedicated time series database and monitoring system, classifies its metrics into distinct types based on how their values are expected to behave. Understanding these types is fundamental to properly collecting and interpreting your data. Counter, definition, a cumulative metric that represents a single monotonically increasing counter. Its value can only increase or be reset to 0 upon a restart of the monitored target. Use cases, counting the total number of HTTP requests, the total number of errors encountered, or the total bytes transferred over a network interface since the process started. Why it matters. You rarely care about the absolute value of a counter, e.g., my web server has served 1 million requests since it started last month. Instead, you care about the rate of change or increase over a period. For instance, how many HTTP requests per second did my server handle in the last minute? Prometheus's query language, PromQL, provides functions like rate and increase to derive these meaningful insights from counters. Gauge, definition, a metric that represents a single numerical value that can arbitrarily go up and down. Use cases, current memory usage, the number of currently active connections, the current temperature of a sensor, or the current number of items in a queue. Why it matters. Gauges represent instantaneous values. If you want to know what your CPU utilization is right now, or how many users are currently logged in, a gauge is the appropriate metric type. Unlike counters, you typically interpret a gauge's raw value directly. Histogram, definition. Histograms are designed to sample observations, such as request durations or response sizes, and count them in configurable buckets. They provide information about the distribution of observed values. How it works. A histogram measures the observed values and counts occurrences in a set of predefined numerical ranges, buckets. For example, it might count how many requests completed in under 0.1 seconds, how many between 0.1 and 0.5 seconds, and so on. A histogram also exposes the total sum of all observed values and the total count of observations. Use cases, analyzing latency distributions for API calls, network packet sizes, or database query times. Why it matters. Averages can be misleading. If your average API response time is 200 milliseconds, that sounds great. But if 99% of requests are 50 milliseconds and 1% are 5 seconds, the average hides a significant problem for a small but important subset of users. Histograms allow you to calculate percentiles, like the 99th percentile latency, giving you a much clearer picture of your system's performance, especially for those tail latencies that impact user experience. Summary. Definition. Similar to histograms, summaries also sample observations, e.g., request durations. However, they calculate configurable quantiles on the client side over a sliding time window. Like histograms, they also expose the total count and total sum of observed events. Use cases, often used for request durations or response sizes where exact quantiles per instance are sufficient, and there is no need to aggregate distributions across multiple instances manually. Why it matters. While providing quantiles, summaries are generally less flexible than histograms for aggregation. If you have many instances of the same service, aggregating histograms across all instances to get a global percentile is a more robust approach than trying to combine quantiles from multiple summaries. As such, histograms are often preferred for most common use cases, particularly in dynamic, distributed environments. Choosing the correct metric type is crucial for effective monitoring and ensures that your data can be queried and interpreted meaningfully in Prometheus and subsequently visualized correctly in Grafana. The open source revolution, Prometheus and Grafana. The shift to cloud-native architectures also coincided with an explosion in powerful, open source tooling. Proprietary monitoring solutions often struggled with the dynamic nature of containerized environments and came with significant licensing costs. This created a fertile ground for projects like Prometheus and Grafana to flourish. Prometheus, born out of SoundCloud in 2012, was specifically designed for the challenges of modern, highly dynamic service-oriented architectures. Its innovative pull model for metric collection, where Prometheus actively scrapes or pulls metrics from exposed endpoints, removed the need for complex agent deployments and made targets easier to manage and debug. Its powerful multi-dimensional data model, where metrics are identified by a name and key-value labels, allowed for incredibly flexible and precise querying. In 2016, Prometheus became the second project to join the Cloud Native Computing Foundation, CNCF, underscoring its pivotal role in the cloud-native ecosystem. Grafana, beginning as an offshoot of the Kibana project in 2014, quickly evolved into the de facto standard for data visualization. Its strength lies in its ability to connect to a vast array of data sources, not just Prometheus, but also Elasticsearch, InfluxDB, PostgreSQL, and many others. It provides a highly intuitive and customizable interface for building interactive dashboards, making complex data accessible and understandable. The synergy between Prometheus and Grafana is what makes them such a powerful duo. Prometheus excels at the backend, efficiently collecting, storing, and providing a powerful query language for time series data. Grafana excels at the front end, taking that raw data and transforming it into compelling, actionable visualizations and alerts. Together, they form the cornerstone of modern observability stacks, providing a comprehensive, flexible, and cost-effective solution for monitoring everything from bare metal servers to complex Kubernetes clusters. In the following chapters, we will dive deep into setting up and leveraging this dynamic duo, starting with the very heart of the system, the Prometheus server itself. Chapter 2, Prometheus, the time series data collector. After exploring the foundational concepts of monitoring and observability, it's time to meet the star of the show, Prometheus. This chapter will delve into Prometheus's unique architecture, guide you through its installation, and help you configure your first targets, including Prometheus itself. You'll also get acquainted with its integral web user interface, your command center for understanding your metrics. Prometheus architecture explained. Prometheus isn't just a database. It's a complete monitoring system designed for reliability and scalability in dynamic environments. Its architecture is built around several key components that work together seamlessly. Prometheus Server. This is the heart of the system. The server's primary responsibilities include scraping, periodically collecting metrics from configured targets; storage, storing collected metrics in its highly efficient time series database, TSDB; rule evaluation, processing recording rules for pre-aggregating data and alerting rules for triggering alerts; querying, responding to PromQL queries from users or tools like Grafana; exporters. Prometheus uses a pull model, meaning the Prometheus server actively pulls or scrapes metrics from HTTP endpoints. This is a significant design choice and a departure from many older monitoring systems that used a push model, where agents send data to a central server. Exporters are essentially small agents or programs that expose existing metrics from third-party systems, like Linux servers, databases, or message queues, in a Prometheus-readable format over an HTTP endpoint, typically on the metrics path. We'll explore these in more detail in Chapter 3. PromQL, the Prometheus query language, is a powerful and flexible functional query language that allows you to select and aggregate time series data in real time. It's what you'll use to ask meaningful questions of your collected metrics. Alert Manager. While part of the Prometheus ecosystem, Alert Manager is a separate component. It handles alerts fired by the Prometheus server, deduplicating, grouping, and routing them to the correct notification receiver, e.g., email, Slack, PagerDuty. It also manages silencing and inhibition, preventing alert fatigue. Service discovery. In dynamic environments, static configuration of targets quickly becomes unsustainable. Prometheus integrates with various service discovery mechanisms, like Kubernetes, AWS EC2, or DNS, to automatically discover and monitor targets as they come online or go offline. The pull model is one of Prometheus's most distinguishing features. Instead of requiring agents to be configured to send data, Prometheus goes out and fetches it. This simplifies target management, just expose the metrics endpoint, and significantly aids in debugging. If Prometheus isn't getting metrics, you can simply try to access the target's metrics endpoint directly from your browser or a command line tool. If you can see the data, Prometheus likely can too, helping pinpoint configuration or network issues quickly. Getting started: installing and running your first Prometheus server. For a hands-on learning experience, we'll install Prometheus directly from its precompiled binaries. This provides a direct understanding of its component parts. Later, in real-world scenarios, you might use Docker containers or Kubernetes deployments, but understanding the basics is crucial. 1. Create a Prometheus user. It's good practice to run Prometheus as a non-privileged user. To add a new system user named Prometheus, without a home directory or a shell, you could execute sudo usered no create home shell bin false Prometheus. 2. Create directories. Prometheus needs directories for its configuration, data, and libraries. Sudo mkdir etc. Prometheus. Sudo mkdir/var/lib/Prometheus. Sudo chown Prometheus. Prometheus var/lib/Prometheus. 3. Download Prometheus. Visit the official Prometheus download page, prometheus.io/download, and get the latest stable version for your operating system, e.g., Linux AMD 64. If you were on a Linux system, you might use wget to download it. Wget https github.com/prometheus/prometheus/releases/download/vxyz-linux-amd64 tar.gz. Replace vxyz with the actual version number. Extract the archive tar xvf Prometheus xyz Linux AMD 64 tar.gz. cd Prometheus xyz Linux AMD 64/. 4. Move binaries and console files. Copy the Prometheus binary and its command line tool, PromTool, to your system's path. Also, copy the consoles and console libraries for the Prometheus web UI. Sudo cp Prometheus /local/bin/. Sudo cp PromTool /local/bin/. Sudo chown Prometheus. Prometheus /local/bin/Prometheus. Sudo chown Prometheus. Prometheus /local/bin/PromTool. Sudo cpr consoles, etc. Prometheus. Sudo cpr console libraries, etc. Prometheus. Sudo chown r Prometheus. Prometheus etc. Prometheus consoles. Sudo chown r Prometheus. Prometheus etc. /Prometheus/console libraries. Understanding Prometheus YAML. Your first configuration. The core of your Prometheus setup is the Prometheus YAML configuration file. This YAML file defines global settings, what targets Prometheus should scrape, and where its alerting rules are located. Let's create a minimal Prometheus YAML that configures Prometheus to monitor itself. Create the file etc. /Prometheus/Prometheus YAML with the following content. Global. How frequently to scrape targets by default. Scrapping interval, 15s. How long until a scrape request times out. Scrap a timeout, 10s. Alert manager configuration. Optional for now, but good to have. Alerting. Alert managers. Static configs. Targets. #localhost:9093 if you install alert manager later. Load rules once and periodically evaluate them. Rule fills. First rule YAML example. We'll cover rules in a later chapter. A list of configurations for scraping targets. Scrape configs. The job name is added as a label job equals job name to all metrics. Scraped from this configuration. Job name. Prometheus. Metrics path defaults to metrics. Scheme defaults to HTTP. Static configs. Targets. Localhost:9090. Prometheus's own metrics endpoint. Labels. Instance. Prometheus server local. Custom label for this instance. Environment. Development. Breaking down the Prometheus YAML. Global. These settings apply to all scrape configurations unless overridden. Scrapping interval. Determines how often Prometheus will attempt to pull metrics from configured targets. Scrap a timeout. The maximum duration Prometheus will wait for a scrape to complete before giving up. Alerting. This section configures the connection to an Alert Manager instance. We've commented out the targets for now as we haven't installed Alert Manager. Rule fills specifies paths to files containing Prometheus recording or alerting rules. We'll dive into rules in a later chapter, so it's noted here for completeness. Scrape configs. This is where you define what Prometheus should monitor. Job name. Every set of targets should belong to a job. This name, e.g., Prometheus, node, web server, is added as a job label to all metrics scraped, helping you categorize your data. Static configs. This is the simplest way to define targets, a static list of hosts and ports. Targets, a list of host, port pairs representing the endpoints to scrape. Here, localhost :9090 is Prometheus's own metrics endpoint. Labels. Any additional labels defined here will be added to all time series scraped from this specific static configs block. These are powerful for adding context like instance, environment, or region. Finally, ensure the Prometheus user owns this configuration file. Sudo chown Prometheus, Prometheus etc. /Prometheus/PrometheusIml. Your first scrape target. Monitoring Prometheus itself. By including localhost :9090 in your scrape configs under the Prometheus job, you've configured Prometheus to monitor its own performance metrics. This is a common and useful practice for ensuring your monitoring system is healthy. Starting Prometheus. Now you can start the Prometheus server. For a quick test, you can run it directly from the command line. Sudo u prometheus usr /local/bin/ Prometheus config file / etc. /Prometheus/PrometheusIml storage tsdb path / var/lib/Prometheus. Sudo u Prometheus runs the command as the Prometheus user. Config file specifies the path to your configuration file. Storage tsdb path tells Prometheus where to store its time series data. This directory must be owned by the Prometheus user. You should see output indicating that Prometheus is starting, scraping targets, and listening on port 9090. For a more robust, production-ready setup, you'd typically run Prometheus as a systemed service. Create a file etc. system Prometheus service. Unit, description equals Prometheus. Once equals network online target. After equals network online target. Service, user equals Prometheus. Group equals Prometheus. Type equals simple. Exec start equals /usr /local/bin/ Prometheus /. Config file equals etc. /Prometheus/PrometheusIml /. Storage tsdb path equals var/lib/Prometheus. Install, wanted by equals multi-user target. Then, reload systemed, enable the service to start on boot and start it. Sudo systemctl daemon reload. Sudo systemctl enable Prometheus. Sudo systemctl start Prometheus. Sudo systemctl status Prometheus. Check the status to ensure it's active, running. Navigating the Prometheus web UI. Once Prometheus is running, open your web browser and go to http localhost :9090. This is the Prometheus web UI, a straightforward interface for interacting with your data and checking the status of your monitoring system. Here are the key sections you'll use. Graph or expression on newer versions. Graph. This is where you'll spend most of your time. You can type PromQL queries directly into the expression input box and then click Execute to see the results. Select the Graph tab for a visual representation over time. Select the Table tab for the raw numerical output. Try it. In the expression box, type Prometheus buildinfo and click Execute. You should see details about your running Prometheus server. Then try Prometheus request total and view it as a graph. Targets. This is an indispensable page for debugging. It shows all the targets Prometheus is configured to scrape, their status, up or DOWN, the last successful scrape time, and any errors encountered. Practical tip. Many times, when a metric isn't showing up as expected, the targets page is the first place to check. For example, a simple typo in a port number in your PrometheuSIML will often result in a DOWN status here with a connection refused error message, instantly pointing you to the problem. Always check this page if your dashboards are empty or misbehaving. Rules. lists all recording rules and alerting rules defined in your configuration files, showing their current state, e.g., pending, firing. Alerts. This page displays the state of any alerts that Prometheus is evaluating. You'll see which alerts are currently firing, triggered, or pending, about to trigger. Please note, this only shows alerts within Prometheus. Alert Manager handles their routing and suppression. Status provides general runtime information about the Prometheus server, including its command line arguments, configuration details, and build information. With Prometheus up and running, and its web UI at your fingertips, you've established the foundation of your observability stack. In the next chapter, we'll expand your monitoring capabilities by introducing Prometheus exporters, allowing you to gather metrics from other essential parts of your system. Chapter 3. Gathering metrics with Prometheus exporters. In Chapter 2, you set up your Prometheus server and configured it to monitor its own essential metrics. But a monitoring system isn't very useful if it only monitors itself. The true power of Prometheus lies in its ability to gather metrics from a vast array of systems and applications. This is where exporters come into play. The exporter ecosystem, what they are and how they work. As we discussed, Prometheus operates on a pull model. It actively scrapes metrics from targets. But not all applications or systems natively expose their metrics in a format Prometheus understands. This is where exporters bridge the gap. An exporter is a small, standalone application or service that translates metrics from a specific system, like a Linux server, a database, or a message queue, into the Prometheus metric format. Once translated, it exposes these metrics over an HTTP endpoint, typically on the metrics path. Prometheus then simply scrapes this endpoint like any other target. Think of an exporter as a universal translator. It speaks the native language of the system it's monitoring, e.g., querying system APIs, parsing log files, reading kernel statistics, and then translates that information into a language Prometheus understands, Prometheus metric format, and serves it over a standard web address. This design is incredibly flexible. If there's an existing system or application you want to monitor, you either find an existing exporter for it, or you or someone else can write one. The Prometheus community maintains a rich and diverse ecosystem of official and third-party exporters for virtually every piece of infrastructure and software you can imagine. Monitoring your servers. Setting up and configuring Node Exporter. One of the most fundamental things you'll want to monitor is the health and performance of your host machines, whether they are physical servers, virtual machines, or cloud instances. The Node Exporter is the go-to solution for this. It exposes detailed hardware and operating system metrics, like CPU usage, memory, disk I/O, network traffic, and file system full alerts from Linux and Unix systems. 1. Create a Node Exporter user. Just like with Prometheus, it's best practice to run Node Exporter as a non-privileged user for security reasons. Sudo userad no create home shell bin false Node Exporter. 2. Download Node Exporter. Visit the Prometheus download page, prometheus.io/download, and locate the Node Exporter binary for your operating system. wget https github.com/prometheus/node-exporter/releases/download/vxyz/node-exporter-amd64 targz. Replace vxyz with the actual version number. tar xvf Node Exporter xyz Linux AMD 64 targz. cd Node Exporter xyz Linux AMD 64/. 3. Move binary. Copy the Node Exporter binary to a system path. Sudo cp Node Exporter usr/local/bin/. Sudo chown Node Exporter. Node Exporter/usr/local/bin/Node Exporter. 4. Create a systemed service file. This ensures Node Exporter starts automatically on boot and runs reliably. Create etc/systemd/system/Node Exporter service. Unit. Description equals Node Exporter. Wants equals network online target. After equals network online target. Service. User equals Node Exporter. Group equals Node Exporter. Type equals simple. Exec start equals /usr/local/bin/Node Exporter. Install. Wanted by equals multi-user target. 5. Start node exporter. Sudo systemctl daemon reload. Sudo systemctl enable node exporter. Sudo systemctl start node exporter. Sudo systemctl status node exporter. Verify that it's running. By default, node exporter listens on port 9100. You can test this by opening your browser to http localhost:9100/metrics. You should see a large amount of raw metric data. 6. Configure Prometheus to scrape node exporter. Now, you need to tell your Prometheus server where to find the node exporter metrics. Edit your etc/Prometheus/PrometheusIml file and add a new scrape configs block. Existing global and alerting sections, scrape configs, job name, Prometheus, static configs, targets, localhost:9090, labels, instance, Prometheus server local, environment, development, job name, node, #new job for host metrics, static configs, targets, localhost:9100, #node exporters port, labels, instance, your server name, give it a descriptive name, environment, production or test, dev, etc. OS, Linux. Remember to replace your server name and production with values appropriate for your environment. These labels will be attached to all metrics coming from this specific node exporter instance, making it easy to identify them later. 7. Restart Prometheus. After modifying PrometheuSIML, you must tell Prometheus to reload its configuration. Sudo systemctl restart Prometheus. 8. Verify in Prometheus web UI. Go to http localhost:9090/targets in your browser. You should now see a new job named node and its target, localhost:9100, listed as UP. Now you can query your node exporter metrics. For example, in the Prometheus Graph UI, http localhost:9090/graph, try typing node seconds total and clicking execute and graph. You'll see the raw CPU time counters, which we'll learn to interpret meaningfully with PromQL in the next chapter. Container visibility, monitoring Docker with cAdvisor. If you're running Docker containers, Google's cAdvisor, Container Advisor, is a simple way to get detailed performance and resource usage information for all running containers on a host. While not officially a Prometheus exporter, it existed before Prometheus. It exposes a Prometheus-compatible endpoint, making it a drop-in monitoring solution. The easiest way to run cAdvisor is as a single Docker container itself. Sudo docker run \, volume =/ /roots row \, volume =/var/run, /var/run, rw \, volume =/sys row \, volume var/lib/docker /var/lib/docker row \, volume =/dev/disk/dev/disk row \, publish =80808080 \, detach true, name =cadvisor \, privileged \, gcr.io/cadvisor/cadvisor:\latest. Let's break down this command. Volume row mounts host directories into the cAdvisor container in read-only mode so cAdvisor can access system and Docker daemon information. Volume var/run /var/run rw mounts the Docker socket needed for cAdvisor to communicate with the Docker daemon. Read-write is required by older Docker versions. Ideally, this would be read-only. Publish =80808080. Maps cAdvisor's internal port 8080 to the host's port 8080. Detach true, runs cAdvisor in the background. Name =cadvisor, gives the container a memorable name. Privileged, grants the container extended privileges, necessary for cAdvisor to access all host resources for monitoring. gcr.io/cadvisor/cadvisor:\latest:, the cAdvisor Docker image. After running this, access http localhost:8080/metrics in your browser. You should see a stream of container metrics. Configure Prometheus to scrape cAdvisor. Add another scrape configs block to your etc/Prometheus/PrometheusIml. Existing sections, scrape configs, Prometheus and node jobs, job name, cadvisor, #new job for cAdvisor, static configs, targets, localhost:8080, #cAdvisor's port, labels, instance, your Docker host, Environment, production. Container engine. Docker. Restart Prometheus and check the targets page in the Prometheus UI. You should now see the CADvisor job listed as up. Now you can query container usage seconds total or container memory usage bytes from the Prometheus Graph UI. Brief introduction to instrumenting applications with client libraries. While exporters handle existing systems, what about your own custom applications? Prometheus provides client libraries for most popular programming languages: Go, Java, Python, Ruby, Node.js, etc. These libraries allow developers to instrument their application code directly to expose custom metrics programmatically. For example, a developer might import the Prometheus client library into their application, define new metrics, e.g., a counter for HTTP request total, a gauge for login users, or a histogram for a pyrespan duration seconds. Increment, set, or observe these metrics within their application's code at appropriate points, e.g., increment HTTP request total every time an HTTP request is processed. The client library automatically exposes these metrics on an HTTP endpoint, e.g., http://your port metrics, which Prometheus can then scrape. This approach offers the greatest flexibility, allowing you to monitor the internal workings and business logic of your applications, providing insights that generic system metrics or logs alone cannot. It's truly a powerful way to make your applications observable from within. Handling ephemeral jobs with Push Gateway and its caveats. Prometheus's pull model works excellently for services and hosts that are long-lived and always available. But what about short-lived batch jobs, cron jobs, or serverless functions that run for a few seconds or minutes and then terminate? By the time Prometheus tries to scrape them, they're gone. For these ephemeral jobs, Prometheus offers the Push Gateway. How Push Gateway works. Instead of Prometheus pulling from the job, the ephemeral job pushes its metrics to the Push Gateway. The Push Gateway then acts as a temporary cache, holding onto these metrics until Prometheus scrapes the Push Gateway. Run Push Gateway, using Docker for simplicity. Docker run d p9091-9091 name Push Gateway prom/Push Gateway. This runs the Push Gateway on port 9091. You can access its web UI at http localhost:9091. It will initially be empty. 2. How ephemeral jobs push data, conceptual. A short-lived script or application would use a Prometheus client library or a simple curl command to send its metrics to the Push Gateway's API endpoint before it exits. For example, a shell script that finishes a task might do something conceptually like this: do a bunch of work. Echo mybitjob duration seconds status equals success. 3.5. Curl data binary at http localhost:9090/meimportantjob/instance/task123. This pushes a metric mybitjob duration seconds to the Push Gateway. The job/meimportantjob/instance/task123 part defines a grouping for these metrics within the Push Gateway. 3. Configure Prometheus to scrape Push Gateway. Add another scrape configs block to your etc/Prometheus/Prometheus-iml. Existing sections, scrape configs, hash, Prometheus, node, CADvisor jobs, job name, Push Gateway. Honor labels. True hash tells Prometheus to not overwrite labels pushed by Push Gateway. Static configs, targets, localhost:9091, hash Push Gateway's port. 4. Restart Prometheus and check the targets page. Prometheus will now scrape the Push Gateway. Any metrics pushed to the Push Gateway will appear under the Push Gateway job in Prometheus. Caveats of Push Gateway. While useful for ephemeral jobs, using the Push Gateway excessively, especially for long-lived services, can introduce several problems. Single point of failure. If your Push Gateway goes down, you lose all metrics from ephemeral jobs that tried to push to it during the outage. Data retention. The Push Gateway retains the last published value for each metric. If a job stops pushing metrics, e.g., deletes itself, the Push Gateway will continue to expose its last known value indefinitely until it's explicitly deleted or the Push Gateway is restarted. This can lead to stale or misleading graphs. Accidental pushes. If not managed carefully, random processes might push data to your push gateway, leading to high cardinality or irrelevant metrics. Practical tip: only use the push gateway for genuinely ephemeral batch jobs where the service isn't alive long enough for Prometheus to scrape directly. For anything else that's long-running, use a direct exporter. You've now learned how to extend Prometheus's reach to collect metrics from your operating systems, your Docker containers, and even your short-lived applications. In the next chapter, we'll unlock the true power of this collected data by diving into the Prometheus query language, PromQL, allowing you to ask sophisticated questions and extract meaningful insights. Chapter 4, Unlocking Data with PromQL, the Prometheus query language. You've successfully set up your Prometheus server and configured it to collect metrics from various sources like itself, your servers via Node Exporter, and potentially your Docker containers via cAdvisor. Now you have a stream of raw, numerical data flowing into Prometheus's time series database. But raw data, while valuable, isn't insight. To transform data into actionable information, you need a powerful tool for querying, filtering, and aggregating it. Enter PromQL, the Prometheus query language. PromQL is a flexible and incredibly powerful functional query language designed specifically for Prometheus's unique time series data model. It allows you to select and aggregate time series data in real time, enabling you to answer complex questions about your system's behavior. PromQL basics: instant vectors, range vectors, and time durations. At its heart, PromQL operates on different types of data. Instant vector. Definition: a set of time series, each containing a single sample, the most recent value for each time series, all sharing the same timestamp. Analogy: a snapshot of current values. Example: goroutines, number of goroutines currently running in Go applications, or node seconds total, the cumulative CPU time from Node Exporter. When you query node seconds total without a time range selector, you get the current value for each CPU and mode. Range vector. Definition: a set of time series, each containing a range of data samples over a specified time duration. Analogy: a history of values over a period. Example: HTT prequest total 5M would return the samples for the HTT prequest total metric over the last 5 minutes. Range vectors are typically used with functions that operate on historical data, like rate or increase. Time durations. Definition: used to specify a time window in PromQL. Units: S seconds, M minutes, H hours, D days, W weeks, Y years. Examples: 5M 5 minutes, 1H 1 hour, 30s 30 seconds. Filtering and matching. Label selectors and common operators. The Prometheus data model relies heavily on labels. Labels are key-value pairs that uniquely identify a time series and add dimensionality to your metrics. PromQL leverages these labels for powerful filtering and matching. Basic selector. The simplest PromQL query is just a metric name, which will return all time series with that name. Node seconds total. Label selectors. You can refine your selection by adding label matchers in curly braces. Equals, equality. Selects labels that are exactly equal to the provided string. Node seconds total job equals node, mode equals idle. Selects idle CPU time from targets in the node job. Equals, non-equality. Selects labels that are not equal to the provided string. Node network transmit bytes to instance equals localhost :9100. Selects network transmit bytes not from the local node exporter. Equals regular expression match. Selects labels that match the provided regular expression. Discrete bytes total device equals tilde SDAZ. Selects read bytes from devices like SDA, SDB, etc. Regular expression non-match. Selects labels that do not match the provided regular expression. HTT prequest total path /API/v0 to 9/. Selects HTTP requests not matching an API path with a version number. Combining selectors. You can combine multiple label matchers, separating them with commas. All conditions must be met, logical and. Node file system avail bytes device equals /dev/SDA1, mount point equals /job equals node. Available bytes on a specific device and mount point from the node job. Aggregation and transformation. Sum, rate, increase, AVG, topk, bottomk. Raw time series data is often too granular. PromQL's aggregation operators and functions allow you to summarize and transform data into meaningful insights. Aggregation operators, using the by and without clauses. These operators reduce the number of time series by aggregating over some labels. Sum calculates the sum across dimensions. Sum node pseconds total by mode. Sum CPU time across all instances, grouped by CPU mode, idle, user, system, etc. Sum HTTP requests total by job, status code. Total HTTP requests broken down by job and HTTP status code. AVG calculates the average. AVG node memory mem total bytes by instance. Average total memory per instance if multiple meminfo metrics exist. Count counts the number of elements. Count node file system avail bytes by instance counts the number of monitored file systems per instance. Min, max, minimum and maximum values. Functions for range vectors. These functions operate on specific time windows, range vectors, and return instant vectors. They are crucial for interpreting counters. Rate, range vector, calculates the per second average rate of increase of the time series in the range vector. This is almost always what you want for a counter. Rate, node network receive a bytes total 5M. Average bytes received per second over the last 5 minutes across all network interfaces. Why needed for counters? A counter just keeps increasing. You rarely care about its absolute value, but rather how fast it's increasing. Rate normalizes it to a per second rate. Increase, range vector, calculates the total increase of the time series over the time range. Increase, HTTP requests total job equals web app, status code equals 200, 1H. Total successful HTTP requests over the last hour. Analogy, if rate is your speed miles per hour, increase is your distance traveled miles. Irate range vector calculates the instantaneous per second rate of increase based on the last 2 data points, more sensitive to short-term spikes. Use rate for robust, smoothed graphing. Delta range vector calculates the difference between the first and last value of the gauge in the range vector. Use only for gauges. Delta node file system avail bytes 1H, change in available file system bytes over the last hour. Functions for ranking, top k expression, returns the top k elements by their metric value. Top 5 sum rate node pseconds total mode equals idle 5M by instance. The 5 instances with the highest average CPU utilization, excluding idle over the last 5 minutes. Bottom k expression returns the bottom k elements. Arithmetic and logic operations. Combining query results. PromQL allows you to combine the results of multiple expressions using standard arithmetic operators, plus, slash, %, and logical set operators, and, or, unless. Arithmetic example. Calculating CPU utilization. CPU usage is typically given in node pseconds total per mode, user, system, idle, IO8. To get CPU utilization as a percentage, you need to sum the non-idle modes and divide by the total CPU time. Total CPU seconds used non-idle. Sum rate, node pseconds total mode equals idle 5M. Total CPU seconds across all modes should be 1 per CPU core per second. Sum rate, node pseconds total 5M. CPU utilization percent. Sum rate node pseconds total mode equals idle 5M. Slash sum rate node pseconds total 5M, 100. This query calculates the average CPU utilization over the last 5 minutes. Vector matching, crucial for multi-series operations. When performing binary operations between 2 instant vectors, PromQL needs to know how to match elements from the left side with elements from the right side. One-to-one matching, when both sides have exactly one element that matches the other by labels. Many-to-one one-to-many matching, uses on or ignoring, clauses to specify which labels to match on or ignore during the operation. This is critical for operations where one side of the query generates fewer time series, e.g., a total sum, combined with per instance metrics. Node file system avail bytes, node file system isobytes 100. This gives the percentage available space for each file system on each instance, assuming the labels match for device, instance, and mount point. This is an example of one-to-one matching where all labels match. Practical PromQL examples. Let's put these concepts into practice with some common scenarios using metrics you're now collecting. 1 current available disk space in GB for the root file system / node file system availbytes mount point equals / 1024 1024 1024. Node file system availbytes mount point equals / selects the bytes available on the root file system / 1024 1024 1024 divides by the number of bytes in a gigabyte to convert to GB. 2 network traffic. Receive bytes per second, last 5 minutes. Sum rate node network receive bytes total 5M by instance device. Node network receive bytes total, the counter for received bytes. 5M, range vector for the last 5 minutes. Rate, calculates the per second rate of increase. Sum, by instance device. If collecting from multiple instances and multiple network devices, sums up rates to get total received bytes per second for each instance and device pair. 3 memory utilization percentage. Node memory, mem total bytes, node memory, mem available bytes, / node memory, mem total bytes 100. Node memory, mem total bytes, total physical memory. Node memory, mem available bytes, memory currently available for new applications. This calculation gives a good proxy for how much memory is actively being used. For top 3 highest CPU utilizing instances, excluding idle CPU. Top 3 sum rate node pseconds total mode equals idle 5M by instance. Node pseconds total mode equals idle 5M, CPU seconds excluding idle mode over the last 5 minutes. Rate. Convert to per second rate. Sum, by instance, sums across CPU cores for each instance to get total non-idle CPU usage per instance. Top 3. Finds the top 3 instances based on this total non-idle CPU usage. 5 HTTP request rate per application and status code. Sum, rate HTTP requests total 1M by job status code. HTTP requests total. A common counter for HTTP requests, assuming your application exposes this. 1M over the last 1 minute. Rate, per second rate, sum, by job status code. Aggregates the request rate, showing the total rate broken down by the application, job, and the HTTP status code. This lets you see the rate of successful requests versus errors. These examples illustrate the power and flexibility of PromQL. It's not just about querying stored data. It's about transforming, aggregating, and comparing it to derive meaningful insights. The beauty of PromQL is its expressiveness, allowing you to formulate precise questions about the behavior of your systems and applications. In the next chapter, we'll take these PromQL queries to the next level by visualizing them in Grafana, transforming cryptic numbers and lines into intuitive, interactive dashboards that tell the story of your system's health. Chapter 5, Grafana, Visualizing Your World. You've mastered the art of collecting metrics with Prometheus and querying them with PromQL. Now it's time to bring that data to life. While Prometheus's own web UI provides a basic graph explorer, it's not designed for creating rich, interactive dashboards or for comprehensive visualization. For that, we turn to Grafana, the leading open-source platform for analytics and monitoring. Grafana is a powerful, flexible, and feature-rich visualization tool that allows you to create beautiful and meaningful dashboards from virtually any data source, including Prometheus. It bridges the gap between raw metrics and actionable insights, making your data accessible to engineers, operations teams, and even business stakeholders. Grafana Overview. Dashboards, panels, data sources, and users. Before we delve into installation, let's understand Grafana's core components. Dashboard. A dashboard is a collection of panels, organized on a grid, designed to visualize multiple metrics related to a specific system, application, or function, e.g., a server monitoring dashboard, a web application performance dashboard. Dashboards can be shared, templated, and are central to how data is presented in Grafana. Panel. A panel is a single visualization unit within a dashboard. Each panel contains a query to a data source and specific display configurations, e.g., a graph showing CPU usage, a single number stat showing error rate, or a table listing top processes. Data source. A data source is a connection to your metrics or logs or traces storage backend. Grafana supports a vast array of data sources, including Prometheus, InfluxDB, Elasticsearch, Loki, MySQL, PostgreSQL, and many more. You configure a data source once, and then any panel can use it. Organizations. Grafana supports multi-tenancy through organizations. Each organization is an independent workspace for users, dashboards, and data sources. This is useful for large companies or service providers who want to isolate different teams or customers. Users and permissions. Grafana has a robust user management system, allowing you to control who can view, edit, or administer dashboards and data sources. Users belong to organizations and can have different roles: viewer, editor, admin. Installation and initial setup. We'll install Grafana directly from its recommended package repositories to ensure easy updates and system integration. 1. Install dependencies. Grafana relies on app transport HTTPS and software properties common for securely handling HTTPS repositories. Sudo apt-get update. Sudo apt-get install y app transport HTTPS software properties common wget. 2. Add Grafana GPG key. This key verifies the integrity of the downloaded packages. Sudo wget qo/share/keyrings/grafana key https apt.grafana.com/gpg key. 3. Add Grafana repository. Add the stable Grafana repository to your apt sources. Echo deb sign by =/usr/share/keyrings/grafana key https apt.grafana.com stable main sudo ta/etc/apt/sources list d/grafana list. 4. Update apt cache and install Grafana. Sudo apt-get update. Sudo apt-get install Grafana. 5. Start Grafana server. Grafana includes a system service by default. Sudo systemctl daemon reload. Sudo systemctl enable Grafana server. Sudo systemctl start Grafana server. Sudo systemctl status Grafana server. Verify that the service is active running. Connecting Prometheus. Setting up your first data source. Now that Grafana is running, we need to instruct it to connect to your Prometheus server. 1. Access Grafana Web UI. Open your web browser and go to http localhost:3000. The default login credentials are username, admin, password, admin. Upon your first login, Grafana will prompt you to change the default password. It's highly recommended to do so for security. 2. Add a new data source. From the Grafana homepage, in the left-hand navigation menu, click on the connections icon looks like two intertwined arrows. Then click Add New Connection. In the Data Source section, search for Prometheus and select it. This will take you to the Prometheus data source configuration page. 3. Configure Prometheus data source. Fill in the following details: name, Prometheus, or any descriptive name like my local Prometheus. Prometheus server URL, http localhost:9090. This is the default address of your Prometheus server. HTTP method, GET. This is the default and typically fine. Leave other settings as default for now. Click the Save and Test button. You should see a green notification. Data source is working. This confirms Grafana can talk to your Prometheus server. Exploring the Grafana web UI. Dashboards, explore, and alerting. Let's briefly tour the main sections of the Grafana UI. Dashboards, left-hand menu, dashboards icon. This is where you'll find and create dashboards. Browse lists all your saved dashboards. New dashboard starts building a dashboard from scratch. Import allows you to import dashboards from JSON files or Grafana's public dashboard repository, grafana.com/grafana/dashboards. Importing pre-built dashboards is a fantastic way to quickly get started with monitoring common software. Explore, left-hand menu, Explore icon. This is Grafana's ad hoc query interface, similar to Prometheus's own Graph UI, but more powerful. It's perfect for developing and testing PromQL queries before adding them to a dashboard. Quickly troubleshooting issues, you can select your Prometheus data source, type a PromQL query, and see the results instantly. Switching between metrics, logs, if you add a Loki data source, and traces, if you add a tempo data source in a single view. Alerting left-hand menu, alerting icon. This section, labeled Alerts, or Alerting depending on your Grafana version, is where you'll define, manage, and view Grafana-managed alert rules. We'll dive deep into this unified alerting system in Chapter 7. Connections left-hand menu, Connections icon, previously configuration. This is where you manage data sources, plugins, and Grafana's core settings. Admin left-hand menu, admin icon visible to admins, manages users, organizations, and provides an audit log. Creating your very first Grafana panel and dashboard. Let's build a simple dashboard to visualize the CPU usage of your server using the node exporter metrics you're now collecting. 1. Create a new dashboard. Click on the dashboard's icon in the left menu. Click New Dashboard. Click Add Visualization. 2. Configure the panel. You'll now be in the panel editor. Select Data Source. At the top right, ensure your Prometheus data source is selected. Enter PromQL query. In the Query section, type the following PromQL query to get the average CPU utilization over the last 5 minutes, excluding idle time. 100 AVG by instance. Rate node ps total mode equals idle 5m, 100. Explanation. This query calculates the percentage of time the CPU is not *idle, averaged over each instance, normalized to 100%. Node ps total is a counter rate, calculates the per second rate of increase over the last 5 minutes. We average AVG by instance if there are multiple CPU cores or modes to get a single line per instance. As you type, Grafana provides auto-completion for metric names and labels. You should immediately see a graph drawing the CPU utilization. 3. Adjust panel settings, optional but recommended. Panel title. At the top, change panel title to CPU utilization. Visualization type. On the right-hand panel, under Visualization, time series is usually the default and correct for this. Units. Under Standard Options for the Value section, set the unit to %, 0 to 100. This will add a % sign to your y-axis and tooltip. Legend. You can expand the legend options to configure how series names are displayed. 4. Save the panel. Click the Apply button, blue button in top right. 5. Save the dashboard. Once back to the dashboard view, click the Save Dashboard icon, looks like a floppy disk at the top of the screen. Give your dashboard a name, e.g., My First Monitoring Dashboard. Click Save. Congratulations! You've just created your first Grafana dashboard and panel, visualizing real metrics from your system. This is a fundamental step. In the next chapter, we'll dive deeper into creating more compelling and dynamic Grafana dashboards, exploring various visualization types, using variables for interactivity, and applying data transformations to enhance your insights. Chapter 6. Crafting Compelling Grafana Dashboards. In the previous chapter, you successfully installed Grafana, connected it to Prometheus, and created your very first panel visualizing CPU utilization. That was just the beginning. Grafana's true power lies in its versatility and extensive customization options, allowing you to transform raw data into visually rich, insightful, and interactive dashboards. This chapter will guide you through choosing the right visualizations, creating dynamic dashboards with variables, and enhancing data with transformations. Choosing the right visualization. Grafana offers a wide array of panel types, each suited for presenting different kinds of data effectively. Selecting the appropriate visualization is crucial for making your dashboards clear, informative, and actionable. Let's explore some of the most commonly used panel types: time series, formerly graph, purpose. The most common visualization, used for plotting time series data over a period. Ideal for showing trends, anomalies, and changes over time. Use cases. CPU usage over time, request rate per second, network throughput, latency trends. Key options. Control line styles, fill, points, axis scaling, thresholds for visual alerts, and series overrides to customize individual lines, e.g., color, line width. Example, your CPU utilization graph from Chapter 5. Stat, purpose, displays a single, prominent numerical value, often with a color-coded background or text based on thresholds. Can optionally include a sparkline mini graph showing recent trend. Use cases, current number of active users, real-time error count, current temperature. Example, a large number displaying your current server's free memory, turning red if it falls below a critical threshold. Gauge, purpose, visualizes a single numerical value as a dial or progress bar, typically with thresholds that define segments. Use cases, disk space utilization percentage, battery level, temperature, or pressure readings. Example, a gauge showing disk usage, turning yellow at 80% and red at 90%. Table, purpose, displays data in a tabular format. Useful for raw data, aggregated results, or showing multiple metrics for discrete entities. Use cases, list of top 10 error rates, breakdown of process memory usage, status of multiple services. Example, a table listing all your monitored hosts with columns for CPU, memory, and disk space. Heat map, purpose, visualizes the distribution of values over time, showing density or frequency. Often used with Prometheus histograms. Use cases, latency distribution over a day, identifying time-of-day performance issues, concurrent user activity. Example, a heat map showing the distribution of API request durations, where darker colors indicate more requests falling into a specific latency bucket at a given time. Bar chart/pie chart, purpose, for categorical data representation, often aggregated. Bar charts show comparisons between categories, while pie charts show proportions of a whole. Use cases, breakdown of HTTP status codes, 2xx, 4xx, 5xx, distribution of services by team. Caution, use sparingly and ensure categories are limited for clarity. Pie charts are often hard to read with many small slices. Advanced panel options, value mappings, map specific numerical values or ranges to descriptive text and custom colors, e.g., 0 to offline, red, 1 to online, green. This is great for status indicators. Overrides, apply specific display settings to individual series within a panel. You can change colors, line styles, and even hide specific series without altering the underlying query. This is useful for highlighting a particular instance or isolating an outlier. Thresholds, define visual alerts on panels by setting value boundaries that change the color of the graph, stat, or gauge. This provides immediate visual cues about the health of a metric. Dynamic dashboards with variables. One of Grafana's most powerful features is variables, also known as templating. Variables allow you to create interactive and reusable dashboards. Instead of hard-coding values into your Prometheus queries, you can use variables that are dynamically populated by external sources, like Prometheus itself, or manually defined lists. Purpose, make dashboards reusable for different environments, services, or instances. Allow users to filter and switch contexts within the same dashboard without editing queries. Reduce maintenance by having fewer, more generic dashboards. Common variable types, query variable, purpose, populated dynamically by a data source query. This is the most common and powerful type. PromQL example. To get a list of all instance labels, hosts, that Prometheus is currently scraping from your node job. Label values, node pseconds total job equals node. Instance. This will create a drop-down in your dashboard with all your node exporter instances. Custom variable, purpose, a manually defined, comma-separated list of values. Use cases, defining environment names dev, staging, prod, or specific service names. Example, dev, staging, production. Text box variable. Purpose, allows the user to type in a free-form value. Use cases, ad hoc filtering, entering a specific ID. Constant variable. Purpose, a hidden variable useful for storing environment-specific constants that you don't want the user to change. Using variables in queries. Once you define a variable e.g., named instance, you can use it in your PromQL queries within panels by enclosing it in curly braces or double square brackets. Instance or instance. Example, making your CPU dashboard dynamic, define the variable, go to Dashboard Settings, cog icon on the top bar, click Variables on the left menu. Click Add Variable. Name, instance. Type, query. Data source. Prometheus, your Prometheus data source. Query, label values, node pseconds total job equals node. Instance. Selection options. Check multi-value and include all option. This allows selecting multiple instances or all of them. Click Add and then Save Dashboard Settings. Update Panel Query. Return to your CPU utilization panel. Click Edit on the panel. Modify the PromQL query to use the new variable. 100 AVG by instance. Rate node pseconds total mode equals idle. Instance equals $$ instance 5M 100. Notice instance equals $$ instance. This uses a regex match equals because the instance variable, when multiple values are selected, becomes a regex string e.g. instance 1 instance 2. If only a single value is selected, equals is fine, but equals handles both cases. Observe the change. Click Apply to return to the dashboard. You'll now see a new drop-down menu at the top of your dashboard for instance. Selecting different instances will dynamically update the CPU utilization graph, enhancing data with transformations. Grafana's data transformations allow you to manipulate or combine data after it's been retrieved from the data source, but before it's visualized in a panel. This is incredibly powerful for refining your data without needing to write complex PromQL. To add a transformation, when editing a panel, go to the Transform tab next to Query. Common transformations. Organize fields, purpose, rename, reorder, or hide fields, columns in your data. Use cases, simplify table views, make field names more user-friendly. Calculate field, purpose. Perform simple mathematical operations or functions between fields or with a single field. Use cases, calculate percentage from two raw numbers, convert units. Example. You could calculate disk utilization percentage from node file system availbytes and node file systems isobytes without needing to use in PromQL if you fetched both raw metrics. Group by purpose. Aggregate rows based on one or more fields and apply aggregation functions, sum, average, count, min, max to other fields. Use cases. Summing up traffic across all network interfaces, calculating average latency per service. Join by field, purpose. Combine results from multiple queries into a single result set if they share a common field. Use cases, combining bytes sent and bytes received metrics into a single total network I/O metric, especially when they come from separate PromQL queries. Example, if query A fetches node network receive a bytes total and query B fetches node network transmit bytes total, you can join them by instance and device to then calculate the sum. Filter by value, purpose. Remove rows time series based on the values in one or more fields. Use cases, filtering out specific statuses, removing very low values. Adding context with annotations. Annotations are small visual markers on your time series graphs that provide context. They are perfect for noting events like deployments, configuration changes, outages, or other incidents that might correlate with changes in your metrics. How to add annotations. Manually from dashboard. Hover over a time series graph, hold Control or CMD on Mac, and click. A pop-up will appear where you can add text and tags. Query-based from a data source, this is more powerful. You can configure an annotation query to automatically pull events from another data source. For Prometheus, you could query metrics related to deployments, e.g., a counter that increments on each deployment, or even the state of Prometheus-fired alerts. To configure an annotation query, go to Dashboard Settings, cog icon, click Annotations on the left menu, click Add Annotation Query, select your Prometheus data source. For example, if you have a metric deployment timeseconds total, you could use deployment timeseconds total as your query pattern. And Grafana will show vertical lines on the graph for each time it increases. Annotations are invaluable for debugging and post-incident analysis, as they help connect what happened with when it happened. Best practices for dashboard design and organization. Crafting effective dashboards is both an art and a science. Here are some best practices. Tell a story. Arrange panels logically, moving from high-level overviews to more granular details. A user should be able to quickly grasp the overall health and then drill down if needed. Simplicity and focus. Avoid wall of graphs dashboards. Each panel should serve a clear purpose and convey specific information. If a dashboard becomes too cluttered, split it into multiple, more focused dashboards. Consistency. Use consistent naming conventions for your dashboards, panels, and variables. Maintain a uniformed color scheme and unit usage. Actionable insights. Dashboards should help answer questions and inform decisions, not just display data. Can a user quickly determine if something is wrong and what might be causing it? Performance. Be mindful of query complexity and the number of queries. Too many complex queries on a single dashboard can slow down load times. Use recording rules in Prometheus, covered in Chapter 8, to pre-aggregate frequently used or computationally expensive queries. Audience-centric. Design dashboards for their intended audience. What an SRE needs might differ from what a developer or a business owner needs. Shared and templated. Leverage variables to make dashboards reusable. Share dashboards within your team or organization to maintain a single source of truth. Documentation. Add text, panels, or dashboard descriptions to provide context, explain metrics, or link to relevant runbooks. You now possess the knowledge to go beyond basic graphs and create rich, interactive, and highly customized Grafana dashboards. These visualizations are your window into the operational health of your systems. However, monitoring isn't just about pretty graphs. It's also about being proactively notified when something goes wrong. In the next chapter, we'll dive into the critical topic of alerting with both Prometheus Alert Manager and Grafana's unified alerting system. Chapter 7. Proactive Alerting with Prometheus and Grafana Unified Alerting. You've built impressive dashboards in Grafana, giving you a clear window into your system's health. But staring at a screen waiting for graphs to spike isn't a sustainable or scalable monitoring strategy. This is where alerting becomes not just useful, but absolutely imperative. Monitoring tells you what is happening. Alerting tells you what needs your attention now. The imperative of alerting, why monitoring isn't enough. Imagine a critical application slowing down gradually, or a server quietly running out of disk space. Without alerts, you might only discover these issues when users start complaining, or worse, when the service completely fails. Reactive monitoring, where you respond only after a problem has become evident, is costly in terms of downtime, customer satisfaction, and team stress. Alerting transforms your monitoring into a proactive defense mechanism. It's the system's way of tapping you on the shoulder and saying, "Hey, something's wrong or about to be wrong, and you need to look at it." Effective alerting focuses on notifying the right people about critical issues quickly, minimizing the impact of incidents. It moves you from "Are we broken?" to "We are broken," and the incident team is already aware and working on it. The goal is not just any alert, but actionable alerts. Too many irrelevant alerts lead to alert fatigue, where teams become desensitized and start ignoring notifications, potentially missing truly critical events. An actionable alert means it indicates a real problem that affects users or system stability. It tells you who needs to respond. It provides enough context to start troubleshooting without immediately logging into a server. Prometheus Alert Manager explained. While Prometheus itself evaluates alert rules, it does not send notifications directly. That crucial task is handled by a separate component, Alert Manager. Alert Manager is designed specifically to manage and dispatch alerts. It receives alerts from one or more Prometheus servers, then processes them based on a sophisticated configuration that allows for grouping. This is one of Alert Manager's most vital features. Instead of receiving dozens or hundreds of individual alerts when a major outage occurs, e.g., a network segment goes down, causing all servers in a data center to become unreachable, Alert Manager groups similar alerts into a single, concise notification. It saves your inbox and sanity. Alerts are grouped based on common labels. Routing. Alert Manager can route alerts to different receivers, e.g., email, Slack, PagerDuty, webhooks, based on their labels. For instance, Critica's alerts might go to your paging system and Slack channel, while warning alerts might only go to Slack. Alerts for the database team can go to their specific channel, while web app alerts go elsewhere. In addition, this prevents redundant notifications. For example, if an entire server is reported as unreachable, Alert Manager can be configured to inhibit, suppress, alerts for services or disks running on that unreachable server. You don't need to know the disk is full if the server itself is down. Silences. For planned maintenance or known issues, you can temporarily silence alerts within Alert Manager for a specific duration or matching a specific set of labels. This prevents unnecessary notifications while you're working on something or expecting an outage. Alert Manager configuration, Alert Manager YAML. The Alert Manager's behavior is defined in its YAML configuration file. It outlines root, the top-level root that defines how alerts are initially processed, including grouping criteria and default receivers. Nested roots can define more specific handling. Receivers, named configurations for various notification channels, email, Slack, webhook, PagerDuty, etc. Inhibit rules, rules to define which alerts should inhibit others. Silences. Although silences are managed via its UI or API, their persistent settings can be configured here. Defining alert rules in Prometheus. Prometheus is responsible for identifying an alerting condition. This is done through alerting rules defined in its configuration. These rules are regular PromQL expressions that, when true, indicate an alert-worthy state. Alert rules are typically placed in separate YAML files, e.g., alert.rulesyml, and loaded by the Prometheus server via the rulefiles directive in Prometheus YAML. A basic Prometheus alerting rule has the following structure: groups, name, my server alerts, rules, alert, instance down hash the name of the alert, expr, up == hash the PromQL expression that defines the alerting condition. 4. 1m hash, how long the expression must be true before the alert fires. Labels, severity, critical hash labels to attach to the alert, used by Alert Manager for routing grouping. Annotations, summary, instance, labels.instance, is down hash human readable summary. Description, labels.instance of job, labels job, has been down for more than 1 minute. Hash detailed description. Key fields explained. Alert, a unique name for this alerting rule. This name is sent to Alert Manager. Expr, the PromQL expression. If this expression evaluates to true, returns a time series with value 1, for any period the alert might fire. 4. This is crucial. It specifies how long the expr must remain true before the alert state changes from pending to firing. This prevents flapping and suppresses brief, transient issues. For example, 4. 1m means the server must be down for a full minute before an alert is sent. Labels, arbitrary key value pairs attached to the alert. These are vital for Alert Manager's grouping, routing, and inhibition rules. Severity is a common label used to prioritize alerts. Annotations, additional informational labels. These aren't typically used for routing, but provide context in the notification. You can use Go template syntax, like labels.instance, to dynamically inject label values into the summary or description. When an alert rule's expression becomes true for the defined for duration, Prometheus sends this alert, with its labels and annotations, to all configured Alert Manager instances. Alert Manager then takes over to group and dispatch notifications according to its own configuration. Grafana unified alerting. In earlier versions, Grafana had its own separate, dashboard-specific alerting system. This was simple but lacked centralized management and robust features. Grafana's unified alerting, introduced in Grafana 8, revolutionizes this by providing a single, consistent alerting system for all its data sources, including Prometheus. Why unified alerting? Centralized management. Create, view, and manage all your alert rules from a single Grafana interface, regardless of the data source. Consistent experience. A single UI for defining conditions, notification channels, and viewing alert states. Multi-source alerts. Leverage alert conditions based on Prometheus queries, Loki logs, Elasticsearch data, SQL query results, etc. Evaluation engine. Grafana includes its own alert evaluation engine, which can evaluate rules internal to Grafana or leverage Prometheus's native evaluation capabilities. This allows for flexible deployment models. Creating an alert rule in Grafana's UI. Access alerting. From the left-hand navigation menu in Grafana, click the Alerting bell icon, then select Alert Rules. New Alert Rule. Click New Alert Rule. Define query and condition. Rule name. Give your alert a descriptive name, e.g. disk spacelo. Data source. Select your Prometheus data source. Query. Enter your PromQL query, e.g., node file system availbytes mount point equals / node file system isobytes mount point equals / 100. Expression condition. Add an expression that evaluates the query result. For example, if your query result is A, you might set a condition A10, meaning if available disk space is less than 10%. 4. Set how long the condition must be met before the alert fires, e.g., 5M. Add details. Summary description. Provide clear, concise information using text and template variables. Labels. Attach labels, e.g., environment, production, team, sysops, severity, warning for routing and grouping. Configure notifications. Link the rule to a notification channel created separately. Grafana's unified alerting can either directly send notifications, if Alert Manager is not configured within Grafana, or it can send its generated alerts to an external Alert Manager instance, like the one you set up earlier. The latter is often preferred, as it leverages Alert Manager's advanced grouping and inhibition features across all your Prometheus and Grafana-generated alerts. Notification channels. A notification channel is a configured endpoint where Alert Manager, or Grafana itself, will send alert messages. Grafana provides native integration with many popular channels. Email, simple and universal, good for less urgent alerts. Slack/Microsoft Teams, excellent for team communication, often used for immediate alerts within a dedicated channel. PagerDuty/OpsGenie/VictorOps, critical for on-call rotations. These services ensure that urgent alerts escalate and reach the right person, even outside working hours. Webhooks. A versatile option for integrating with custom scripts, internal tools, or other messaging platforms. Discord, Telegram, Pushover, other popular messaging services. Configuring a notification channel in Grafana. From the left-hand navigation, go to Alerting, Bell icon, Contact Points. Click New Contact Point. Choose a type, e.g., Slack. Fill in the specific details, e.g., Slack webhook URL, recipient channel. Click Save Contact Point. You can then link this contact point to alert rules or define notification policies that route alerts based on labels. Practical examples of alert rules. Let's look at setting up crucial alerts you'll likely use in your environment. 1. High CPU usage, Prometheus alert rule. This rule alerts when a server's CPU utilization, specifically non-idle time, consistently exceeds 90% for 5 minutes. In your alert.rules, IML or similar file loaded by Prometheus, groups, name, host resource alerts, rules alert, high CPU usage, expr, sum rate, node seconds total mode equals idle 5M, by instance, 0.90. 4. 5M, labels, severity, warning, team, infrastructure, annotations, summary, high CPU usage detected on labels.instance. Description, labels.instance, has been consuming more than 90% CPU for the last 5 minutes. Consider checking active processes or scaling up. After adding this, remember to reload your Prometheus configuration, sudo systemctl reload Prometheus. 2. Disk full, Grafana unified alert. This rule alerts when a server's root file system has less than 10% available space for 10 minutes. Create this directly in Grafana's UI. Rule name, host disclose space. Data source, Prometheus. Query, A, node file system availbytes mount point equals / B, node file system's isobytes mount point equals / C, a /B100. This calculates percentage available. Condition, C is less than 10. For 10M, 10 minutes. Labels, severity, critical department, operations. Annotations, summary. Disk space low on, labels.instance. Description, the root file system on labels.instance has less than 10% space available. Current usage. Print %.2f, 100 value C, %, note the use of values, C to reference the result of query C. Contact points. Link to your chosen contact point, e.g., Slack channel operations. 3. Service down, Prometheus alert rule. This essential alert fires if a critical monitoring target, like your web application or database, stops exposing metrics for 1 minute. Prometheus's up metric, which is 1 if a target is up, 0 if it's down, is perfect for this. In your alert.rules IML, groups, Name, application availability. Rules, alert, application service down. Expr, upjob equals myweb equals 0. For 1M, labels, severity, critical. Team, web app. Annotations, summary. Application labels job on instance, labels.instance is down. Description, the labels job application on host, labels.instance, has been unreachable for 1 minute. Investigate immediately. Reload Prometheus after adding. Alerting best practices. Alert on symptoms, not causes. This is a golden rule. Instead of alerting on database disk is 90% full, alert on queries to the database are failing slowing down. The symptom directly impacts the user. The cause, disk full, is something you investigate after the symptom alert fires. Define clear playbooks/runbooks. For every alert, have a document that explains what it means, why it's firing, and the initial steps to mitigate or resolve the issue. Review and tune regularly. Alerts should evolve with your system. Regularly review alert effectiveness, remove noisy or irrelevant alerts, and refine thresholds. Use different severities. Not all alerts are created equal. Use critical, warning, info severities to differentiate urgency and route them appropriately. Consider the golden signals. For applications, focus your primary alerts on these 4 metrics. Latency, how long requests take. Traffic, how much demand is being placed on your system. Errors, the rate of failed requests. Saturation, how full your system is. Resource utilization. These are direct indicators of application health from a user's perspective. By thoughtfully crafting your alert rules and leveraging Alert Manager and Grafana's unified system, you can transform your monitoring from a reactive chore into a proactive operational advantage, ensuring your team is informed and empowered to address issues before they impact your users. Chapter 8, Advanced Prometheus, Scaling and Discovery. You've now mastered the fundamentals of Prometheus and Grafana. From collecting metrics and querying them with PromQL to building dashboards and defining alerts. These foundational skills are sufficient for monitoring a small to medium-sized environment. However, as your infrastructure grows, becoming more dynamic and distributed, you'll encounter new challenges related to target discovery, configuration management, and query performance. This chapter will delve into advanced Prometheus features designed to address these challenges, enabling you to scale your monitoring and optimize your data. Automating target discovery. The power of service discovery. In a static environment, manually listing targets in Prometheus using static configs works fine. But in modern cloud-native architectures where services are ephemeral, scale up and down dynamically, and change IP addresses frequently, relying on manual configuration is impossible. You need Prometheus to automatically discover its targets. Prometheus provides a rich set of service discovery integrations to accomplish this. Instead of a fixed list of targets, you configure Prometheus to connect to a service's API, e.g., Kubernetes, AWS EC2, DNS, and dynamically pull a list of active targets. Here are some common service discovery mechanisms. File-based service discovery. How it works. You configure Prometheus to watch a set of files, e.g., JSON or YAML format, for changes. An external process or script maintains these files, updating them with current target information. Use cases. Simple dynamic environments, integrating with custom inventory systems that can output files, or when native service discovery isn't available. Example snippet in Prometheus scrape configs, job name, my app, files configs, names, etc. /Prometheus/target/myapptargets.json. Refresh interval. 5M hash, check the file every 5 minutes. The myapptargets.json file would look something like this. Targets 192.168.1.10:8080. 192.168.1.11:8080. Labels. Environment, production. App is my app. Targets 192.168.1.12:8080. Labels. Environment, staging. App, my app. Kubernetes service discovery. How it works. Prometheus queries the Kubernetes API server to discover pods, services, endpoints, ingress controllers, and nodes. This is extremely powerful for monitoring Kubernetes clusters. Kubernetes automatically attaches various labels to discovered targets, e.g., pod name, namespace, container name, providing rich context. Use cases: monitoring applications deployed in Kubernetes clusters. Example snippet simplified, scrape configs, job name, Kubernetes pods, Kubernetes configs, role, pod, relabel configs, source labels, meta Kubernetes pod annotation Prometheus scrape. Action, keep. Regex, true hash only scrape pods with a specific annotation. Source labels, address, meta Kubernetes pod annotation Prometheus port. Action, replace. Regex, +D+, replacement, $1.2. Target label, address hash rewrite the address to use the annotated port. Note, Kubernetes service discovery configurations are often much more complex, involving extensive relabeling to filter and transform the discovered targets to fit your monitoring needs. Oz EC2 Service Discovery. How it works. Connects to the EC2 API to discover instances dynamically, allowing you to filter by tags, regions, states, etc. Use cases: monitoring instances in AWS environments. DNS service discovery. How it works. Prometheus performs DNS lookups, e.g., SRV records, to find targets. Use cases: simple load balance services, or when you have external systems managing DNS records. When using service discovery, Prometheus attaches a rich set of metadata labels, prefixed with meta, to discovered targets. These temporary labels are then processed by relabeling rules to decide whether to scrape a target, modify its metrics before storage, or rewrite its final labels. Relabeling and metric manipulation. Relabeling is arguably one of the most complex yet powerful features in Prometheus. It allows you to dynamically rewrite, add, or drop labels on targets before scraping, and on metrics after scraping, but before internal processing. It's often used in conjunction with service discovery to filter targets or clean up labels. A relabel config block consists of source labels, a list of labels whose values are used as input to the regular expression. These can be temporary meta labels from service discovery or existing labels. Regex, a regular expression to match against the concatenated values of source labels. You can capture parts of the regex using parentheses. Target label, the label to which the output of the matching action is written. Temporary labels prefixed with are often used here. If target label is prefixed with, it's not stored in the final metric. Replacement, the string that replaces the part of the source labels that match the regex. Back references, $1, $2, etc. can be used from the regex captures. Action, what to do if the regex matches or doesn't match. Common actions include replace, default, replace the target label with the replacement string. Keep the target or metric if the regex matches, drop it otherwise, used for filtering. Drop the target or metric if the regex matches, keep it otherwise, also used for filtering. Label map a set of source labels to target labels based on a regex. Label drop all labels matching the regex. Label keep, drop all labels not matching the regex. Example, filtering and adding custom labels from EC2 tags. Imagine you use EC2 service discovery and your instances have tags like env, production and service. Web app, scrape configs, job name, ec2 app, ec2sd configs, region, us east 1. Hash role credentials needed, if not run on EC2, instance, with proper IAM role. Hash relabeling rules for targets, before scraping. Relabel configs, hash keep only instances where the env tag is production. Source labels, medec2 tag env. Regex, production. Action, keep. Hash add environment label from EC2 tag, env. Source labels, medec2 tag env. Regex, target label, environment. Replacement, $1. Hash add service, label from EC2 tag, service. Source labels, medec2 tag service. Regex, target label, service. Replacement, $1. Hash metric relabeling rules, after scraping, before storage. Metric relabel configs, hash drop the instance label from the scraped metrics, if not needed. Source labels, instance. Action, drop. This example shows how relabel configs process discovered targets, and metric relabel configs manipulate labels on the metrics themselves. Recording rules, pre-aggregating data for performance and complex queries. Prometheus calculates query results on the fly, while powerful, complex, or frequently executed queries, especially those over long time ranges or involving many time series, can put a significant load on your Prometheus server and slow down dashboard loading. Recording rules solve this by allowing you to pre-compute frequently needed or expensive PromQL expressions and save their results as new time series. These new time series are then scraped by Prometheus just like any other metric. Benefits of recording rules: performance improvement. Dashboards and alerts become faster because they query the pre-calculated, simpler time series instead of recalculating complex expressions every time. Simpler queries. Your PromQL queries in Grafana or alerts become much simpler, referencing the new metric name rather than the full complex expression. Foundation for alerts. Often, recording rules are used to create service-level metrics, e.g., application error rate, critical latency percentile, that are then used directly in alerting rules. Structure of a recording rule. Recording rules are defined in separate rule files, e.g., rulesyml, which are referenced in Prometheus YML under rulefills. Groups. Name, application metrics. Rules, record. Job HTTP request total rate 5m hash new metric name pattern. Level metric aggregation. Expr sum rate HTTP request total 5m. By job, status code, hash the expression to pre-compute. Labels, tier. API hash optional. Add static labels to the new series. Name, resource utilization. Rules, record. Instance, node utilization ratio. Expr 1 AVG by instance. Rate, node seconds total mode equals idle 5m. In the record field, it's good practice to follow a naming convention like level, metric name, aggregation or ratio. After defining a recording rule, a new metric, e.g., job, HTTP request total rate 5m, will appear in Prometheus and can be queried like any other metric. Your Grafana panels or alert rules can then simply use this new pre-computed metric. Federation, simple scaling for Prometheus. While Prometheus is designed to be highly scalable vertically, handling millions of active time series on a single server, sometimes you need horizontal scaling for organizational or architectural reasons, e.g., multiple clusters, different teams, geographic distribution. Federation is Prometheus's basic mechanism for collecting selected time series from one Prometheus server into another. How it works. A global, or aggregating, Prometheus server scrapes specific metrics from one or more regional, or leaf, Prometheus servers via their federation endpoints, federate. The leaf servers expose only a subset of their metrics, usually recorded rules or critical raw metrics, to the global server. Regional Prometheus server, leaf, scrapes its local targets, exposes a federate endpoint, http://leaf Prometheus, 1990/federate, match equals job equals node, instance equals instance 1, and match equals job equals API. This is the query the global server would make. Global Prometheus server, configured to scrape the federated endpoints of the leaf servers. Scrape configs, job name, federate. Scrapping interval, 1m hash scrape less frequently. Honor labels, true hash crucial. Don't overwrite labels from the source Prometheus. Metrics path, federate. Params, match, hash which metrics to pull from the leaf server. Name equals tilde job, hash all recorded rules. Name equals up, hash the up metric for all targets. Static configs, targets leaf Prometheus, 1990. Labels, cluster. US West 1, hash custom label to identify the source cluster. Use cases for federation, centralized view. Get a top-level view of health across different clusters or environments without needing to run a single monolithic Prometheus server. Cross-cluster alerting. Define global alerts that fire based on metrics from multiple regional Prometheus instances. Data isolation. Keep detailed, high-resolution metrics locally on regional servers, while only forwarding aggregated, high-level metrics to the global server. Limitations. Federation is a relatively simple copying mechanism. It's not a distributed storage solution. It doesn't solve long-term retention or global querying of all raw data from all Prometheus instances. For these problems, more advanced solutions are needed. Introduction to remote storage Thanos, Cortex, for long-term storage and scalability. Prometheus's local storage is highly efficient for short to medium-term retention, weeks to a few months. However, for long-term historical data, global query views across clusters, and robust high availability, remote storage solutions are needed. Projects like Thanos and Cortex extend Prometheus's capabilities by providing long-term storage, persist metric data in object storage, e.g., S3, GCS for years decoupled from local Prometheus servers. Global query view. Query data seamlessly across multiple Prometheus instances and long-term storage, as if it were one massive Prometheus instance. High availability. Ensure monitoring continues even if a Prometheus server goes down, with redundant ingestion and query paths. Data deduplication. Handle multiple replicas of Prometheus scraping the same targets without storing duplicate data. These solutions enable building a truly enterprise-grade, highly available, and scalable observability platform around Prometheus. While beyond the scope of this book for in-depth setup, understanding their purpose is crucial for planning your Prometheus deployment at scale. Thanos and Cortex primarily work by implementing Prometheus's remote write and remote read APIs, allowing Prometheus to send its data to an external system and query data from it. By leveraging service discovery to manage targets automatically, applying relabeling to tailor your metric landscape, using recording rules to optimize query performance, and understanding the role of federation and remote storage for scaling, you are now equipped to build a robust and resilient monitoring infrastructure with Prometheus, capable of handling dynamic and complex environments. Chapter 9: Real-World Scenarios and Best Practices. You've built a solid foundation, understanding Prometheus and Grafana's core functionalities, from installation and data collection to powerful querying, visualization, and alerting. Now, it's time to bridge the gap between theory and practice. This chapter will focus on applying these tools to real-world scenarios, leveraging best practices, and developing a holistic observability culture within your team. The golden signals: monitoring applications. When monitoring applications, especially complex distributed systems, it's easy to get lost in a sea of metrics. The golden signals provide a concise, high-level framework for effective application monitoring, focusing on what directly impacts users and business outcomes. These signals were popularized by Google in their Site Reliability Engineering (SRE) book and are applicable to almost any service. The 4 golden signals are: latency, definition, the time it takes to serve a request. What to monitor, focus on both successful and failed request latencies. Also, distinguish between average latency, which can be misleading, and percentiles, e.g., P90, P99, which give a truer picture of user experience, especially for tail latency. Prometheus metrics, typically measured using histograms, e.g., HTTP request duration seconds bucket. PromQL example: histogram quintile 0.99, rate HTTP request duration seconds bucket 5M, for 99th percentile latency over 5 minutes. Alerting, alert if P99 latency for critical endpoints exceeds a threshold, e.g., 2 seconds. Traffic, definition, how much demand is being placed on your system. This is an indicator of load. What to monitor. Requests per second RPS, total bytes transferred, concurrent users, active sessions. Prometheus metrics, typically measured using counters, e.g., HTTP requests total, network bytes total. PromQL example: sum rate HTTP requests total 1M by job, RPS per application. Alerting, alert if traffic unexpectedly drops, a potential outage or spikes, a potential overload or attack. Errors, definition, the rate of requests that fail. What to monitor. HTTP 5xx errors, application-specific error codes, exceptions, failed transactions. Prometheus metrics, typically derived from counters with a status code or result label, e.g., HTTP requests total status code equals ~5. PromQL example: sum rate HTTP requests total status code equals ~5, 1m/sum rate http prequest total 1m 100% of 5xx errors. Alerting. Immediate critical alert for any sustained increase in error rate or exceeding a low threshold, e.g., 1%. Saturation. Definition: how full your system is. This indicates how close a resource is to its limits. What to monitor: CPU utilization, memory usage, disk I/O, network bandwidth, database connection pool usage, queue depth. Prometheus metrics. Often gauges, e.g., node queue seconds total, node memory mem available bytes. PromQL example: node memory mem total bytes, node memory mem available bytes, / node memory mem total bytes 100, memory usage percentage. Alerting. Warning alerts when saturation approaches critical levels, e.g., CPU consistently above 80%, disk above 90% full. By focusing your dashboards and primary alerts on these 4 signals for each critical service, you ensure comprehensive, high-leverage monitoring that directly correlates to user experience and operational stability. Capacity planning. Using historical metrics to predict future needs. Monitoring isn't just for reactive troubleshooting. It's also invaluable for proactive planning. Prometheus's long-term data collection makes it an excellent source for capacity planning. By analyzing historical trends, you can predict when your current infrastructure will reach its limits and plan for scaling before performance degrades. How to use Prometheus for capacity planning. Identify growth trends. Look at key saturation metrics, e.g., CPU, memory, disk, database connections, network bandwidth, over the past weeks or months. Use Grafana's graphing capabilities to visualize these trends. PromQL for trend. For a resource like CPU, look at avgovertime, instance, node utilization, ratio 6W, to see the average utilization over the last 6 weeks and how that has changed. Estimate growth rate, quantify the increase. Is it linear, exponential, or seasonal? Project future usage. Based on the observed growth rate, extrapolate future resource requirements. Define a buffer. Always plan with a safety margin, e.g., 20 to 30% additional capacity to account for unexpected spikes or inaccurate predictions. Set alerts for nearing capacity. Configure warning alerts that trigger when a resource is projected to hit a critical threshold within a certain timeframe, e.g., disk expected to be 95% full in next 2 weeks. This requires PromQL's predict linear or Holt-Winters functions, which are more advanced. Example, simplified, use with caution. Predict linear, node file system avail bytes mount point equals /1d 43600 0, predicts if disk will run out of space in 4 hours based on last 1 day's trend. Practical tip. Combine capacity planning with business growth forecasts and product roadmaps to ensure your infrastructure scales alongside your user base and feature development. Troubleshooting workflows. Leveraging dashboards for incident response. When an alert fires, your monitoring dashboards become your primary tool for incident response. A well-designed troubleshooting workflow using Grafana can drastically reduce mean time to resolution, MTTR. A typical workflow: alert receives, an alert fires, e.g., high error rate on web app. Initial triage, overview dashboard. The alert notification should link directly to a relevant overview dashboard. This dashboard should immediately show the golden signals for the affected service, providing a quick health check. Are all signals red, or just one? What to look for: correlations. Did traffic spike right before errors? Did latency increase? Drill down component-specific dashboards. From the overview, if, for example, the error rate is high, you'd navigate to a more detailed web app error dashboard. This dashboard would have panels breaking down errors by type, endpoint, HTTP status code, or even host. Use Grafana's time range selector and variable filters, e.g., select only the instance that's failing to narrow down the scope. Contextual information, logs, and traces. If metrics show a problem but don't pinpoint the root cause, jump to logs and traces. Grafana Loki integration. If you're using Loki for logs, you can often click from a metrics point to see logs around that time, helping to explain the metric's behavior, e.g., error rate went up because a new deployment failed to start. Grafana Tempo Jaeger integration. For microservices, Trace IDs from errors in logs can be used to initiate a trace lookup, showing the full path of a failing request across all services. Hypothesis and remediation. Based on the data, form hypotheses, test them, and apply remedies. Iterate using your dashboards to observe the impact of your changes. Postmortem/learning. After resolution, use the historical data in Grafana to conduct a postmortem. What happened? How quickly was it detected? How quickly was it resolved? What can be learned to prevent recurrence or improve response? Dashboards as code. Maintaining configurations with Git. As your monitoring setup grows, managing Prometheus YAML, alert.rules, and Grafana dashboards manually becomes cumbersome and error-prone. Dashboards as code (DAC), or more broadly, configuration as code, applies version control principles, like Git, to your monitoring configurations. Benefits: version control. Track changes, revert to previous versions, and understand who changed what and why. Collaboration. Teams can collaborate on monitoring configurations using standard Git workflows, pull requests, code reviews. Automation. Integrate configuration changes into your CI/CD pipeline, ensuring consistency between deployments and monitoring readiness. Reproducibility. Easily spin up new monitoring environments identical to existing ones. Tools and approaches. Prometheus. Your Prometheus YAML and rules YAML files should always be in version control. You can use simple scripts or tools like Ansible/Chef/Puppet to push these configurations to Prometheus servers. Grafana, built-in provisioning. Grafana can be configured to load dashboards from files on disk at startup. This means you can store your dashboard JSON files, exported from Grafana or created manually, in a Git repository. Create JSON files for your dashboards. Configure Grafana's grafana.ini to point to a provisioning directory, e.g., /etc/grafana/provisioning/dashboards. Place a YAML file in that directory, pointing to your dashboard JSON files. Grafana API. While less common for simple DAC, you can use the Grafana API client libraries, e.g., Grafana Client for Python, or tools like Grafana Tool to manage dashboards programmatically. JSONit/Terraform. For advanced users, tools like JSONit allow you to programmatically generate Grafana dashboard JSON, providing more flexibility and less repetition than raw JSON. Terraform can manage Grafana resources, dashboards, data sources, alert rules directly. Practical tip: start with basic Git version control for your Prometheus config and Grafana JSONs. Avoid manually editing Prometheus YAML or dashboards directly on production servers. Structuring your Prometheus configuration and Grafana dashboards for maintainability. Good organization is key to a manageable monitoring system. Prometheus configuration, Prometheus YAML and rule files, modular scrape configs, keep related job name blocks together. Separate rule files, don't put all rules in one giant file. Group them logically, e.g., hostalert YAML, appalert YAML, recording rules YAML. Consistent naming, use clear, consistent job name values and metric names. Comments. Use comments to explain complex relabel configs or PromQL expressions. Grafana dashboard organization. Folders. Use Grafana folders to organize dashboards by service, team, or environment, e.g., web app, database, dev environment. Consistent naming. Use clear, descriptive dashboard titles. Templated dashboards. Design dashboards to be as generic and reusable as possible using variables, instance, job, etc. Avoid duplicating dashboards. Use variables to create views for different systems. Readability. Use clear panel titles, units, and legends. Organize panels logically. Dashboards versus alerts. Remember, dashboards are for exploration and troubleshooting. Alerts are for notification. Don't rely on someone looking at a dashboard to detect a problem. The human element, observability culture, and team collaboration. Technology alone won't create an observable system. It requires a shift in culture and active collaboration. Shared ownership. Monitoring and observability should not be solely the responsibility of an operations or SRE team. Developers, QA, and even product managers should understand and contribute to what gets monitored and why. Definition of done. Make instrumentation and observability a part of your definition of done for any new feature or service. Blameless postmortems. Use monitoring data to understand system behavior and identify systemic weaknesses, not to assign blame. Documentation. Document your monitoring setup, what key metrics mean, and common troubleshooting steps. Training. Educate your engineers on PromQL, Grafana, and how to use the dashboards for self-service debugging. Feedback loop. Regularly solicit feedback on the quality and usefulness of alerts and dashboards. Are they too noisy? Are they missing critical information? By fostering a culture where everyone is invested in observability, you transform monitoring from a reactive burden into a powerful tool for understanding, improving, and ensuring the reliability of your systems. In the final chapter, we'll explore how Prometheus and Grafana fit into the broader observability landscape and where to go for continued learning. Chapter 10. Beyond the Basics. Extending your monitoring ecosystem. Congratulations! You've come a long way from understanding basic monitoring to proficiently configuring Prometheus and Grafana for robust observability. You can now collect, query, visualize, and alert on a wealth of metrics, providing deep insights into your systems and applications. However, the world of observability is vast and ever-evolving. This final chapter will briefly touch upon how Prometheus and Grafana integrate with other tools to form a more complete observability stack, hint at future trends, and guide you towards continuing your learning journey. Exploring the rich Prometheus and Grafana ecosystem. One of the greatest strengths of both Prometheus and Grafana is their vibrant open-source communities and extensive ecosystems. Community exporters. Beyond the official node exporter and cAdvisor, there are hundreds of community-contributed exporters for almost every piece of technology imaginable. Databases, MySQL, Postgres, MongoDB, message queues, Kafka, RabbitMQ, web servers, Nginx, Apache, cloud services, and more. A quick search for Technology Exporter Prometheus will often yield a working solution. This drastically reduces the effort required to get basic monitoring in place for common software. Grafana plugins. Grafana's functionality can be extended through a rich plugin architecture. Panel plugins introduce new visualization types beyond the core ones, e.g., world maps, calendars, status maps. Data source plugins allow Grafana to fetch data from even more sources beyond the officially supported list. App plugins provide more integrated experiences, combining data sources, dashboards, and custom interfaces. You can browse and install plugins directly from the Grafana UI or the Grafana Labs website. Leveraging these community-driven tools allows you to tailor your monitoring solution to your specific technological stack and organizational needs without reinventing the wheel. Integrations with logs, the Grafana Loki stack. While Prometheus excels at metrics, it purposefully leaves logs and traces to other specialized tools. However, modern observability advocates for bringing these pillars together for a comprehensive view. Grafana Loki is a popular choice for integrating logs into your Grafana dashboards, offering a powerful, cost-effective, and Prometheus-inspired approach to logging. Loki's philosophy. Loki is not like traditional log aggregation systems. Instead of full-text indexing every log line, Loki indexes only metadata, labels, about log streams. This makes it significantly cheaper and faster to operate. How it works. PromTail. A lightweight agent, similar to a Prometheus exporter that runs on your servers, scrapes logs from various sources, files, system journal, Docker logs, and attaches Prometheus-like labels to them before pushing them to Loki. Loki stores log data, often in object storage like S3 or GCS, and its associated labels. LogQL. Loki's query language, which is inspired by PromQL. You use LogQL to filter log streams by labels and then perform additional text filtering. Grafana integration. Loki is built to be tightly integrated with Grafana. You add Loki as a data source and can then query and visualize log volumes, similar to metrics, using LogQL. Use the Grafana Explore view to switch seamlessly between metrics from Prometheus and logs from Loki for easier debugging, leveraging shared labels. Drill down from a metric spike to relevant log lines, providing crucial context why a metric changed. The combination of Prometheus and Loki in Grafana creates a powerful metrics and logs observability solution where both data types provide mutual context. Introduction to tracing, Jaeger and Grafana tempo. While metrics tell you what is happening and logs tell you where or when something happened, traces tell you how a request flows through and behaves within your distributed system. Tracing is critical for understanding latency bottlenecks and identifying failures across microservice boundaries. OpenTelemetry. This emerging standard aims to provide a unified set of APIs, SDKs, and data specifications for generating and collecting telemetry data, metrics, logs, and traces. It simplifies instrumentation efforts by providing a single framework. Jaeger, an open-source, end-to-end distributed tracing system that helps monitor and troubleshoot transactions in complex distributed systems. It collects, stores, and visualizes trace data. Grafana Tempo, a high-volume, cost-efficient, and easy-to-use open-source distributed tracing backend, also designed for Grafana. Like Loki, Tempo indexes traces based on their trace IDs, not their full content, allowing for very cheap trace storage, often in object storage. Grafana integration. Just like Loki, Tempo, or Jaeger, can be added as a data source in Grafana. This allows you to fetch traces directly via their trace ID, integrate trace IDs into your logs via Loki or metrics from Prometheus, allowing you to jump from a metric error or log message directly into the full trace to see the exact execution path of a problematic request. By adding tracing with tools like OpenTelemetry, Jaeger, and Grafana Tempo to your Prometheus and Grafana setup, you achieve the 3 pillars of observability and gain unparalleled visibility into your distributed applications. The future of observability. What's next? The observability landscape is dynamic, with continuous innovation and evolving best practices. Here are a few trends and concepts to watch. OpenTelemetry adoption. OpenTelemetry is rapidly becoming the industry standard for telemetry data collection. Expect more tools and platforms to natively support it, simplifying agent deployment and instrumentation. AI Ops, artificial intelligence for IT operations. Leveraging machine learning to analyze monitoring data, predict outages, identify anomalies, and even suggest root causes, reducing the burden on human operators. Evolving data models. More sophisticated data models are emerging that can combine metrics, logs, and traces at a deeper level for richer analysis. Shift-left observability. Moving observability concerns earlier in the software development lifecycle, empowering developers with insights into their code's performance and behavior from the very beginning. Edge and IoT monitoring. As computing extends to the edge and the proliferation of IoT devices, monitoring these distributed, often resource-constrained environments presents unique challenges and opportunities. Recommended resources for continued learning and community engagement. This book has provided a comprehensive foundation, but your learning journey doesn't end here. The best way to deepen your expertise is through continued exploration and community engagement. Official documentation, Prometheus documentation, your definitive source for all things Prometheus. Grafana documentation, comprehensive guides for Grafana. PromQL documentation, dive deeper into PromQL's nuances. Alert Manager documentation for advanced Alert Manager setups. Blogs and articles, Grafana Labs blog. Regularly features new features, best practices, and use cases. Prometheus blog, updates from the Prometheus development team. Other DevOps/SRE blogs. Many industry leaders and companies share valuable insights, e.g., Google Cloud blog, AWS, Red Hat, Datadog's engineering blog. Community forums and chat, Prometheus community on Slack Discord. Active users and developers. Grafana community forums, ask questions, share insights. Conferences, PromCon, the official Prometheus conference. Grafana Con, the official Grafana conference. KubeCon plus Cloud Native Con, features many talks on Prometheus, Grafana, and related cloud-native technologies. Many past talks are available online. Books. Continue exploring more advanced SRE principles, distributed systems, and specific tool deep dives. Hands-on practice. The best way to learn is by doing. Set up personal labs, experiment with new exporters, build dashboards for your pet projects, and break things safely to understand how they work. Observability is a continuous journey of understanding, adapting, and improving. You now have the skills and knowledge to navigate this journey effectively with Prometheus and Grafana as your trusted companions. Embrace experimentation, engage with the community, and never stop questioning what's really happening inside my systems. Happy monitoring. Chapter 11, Security and Performance Considerations. Having built a robust monitoring system, it's crucial to acknowledge two areas that, if neglected, can undermine all your efforts: security and performance. A powerful monitoring system that is vulnerable to attack or that consumes excessive resources can quickly become a liability rather than an asset. This chapter will guide you through essential security practices and key performance considerations for your Prometheus and Grafana deployments. Securing your Prometheus and Grafana deployments. Security is paramount. Exposed monitoring data or vulnerable endpoints can be exploited to reveal sensitive system information or even provide attack vectors. 1. Network segmentation and firewall rules. Restrict access to Prometheus server. Prometheus's web UI and API, port 9090 by default, should ideally not be exposed directly to the public internet. Restrict access to internal networks, VPNs, or specific IP ranges. Use firewall rules, e.g., UFWA, firewalled AWS security groups, to achieve this. Example UFW rule. Sudo UFWA allow from 192.168.1.0/24 to any port 9090, allowing access from your internal network. Restrict access to exporters. Similarly, limit access to node exporter, default port 9100, and other exporter endpoints. Only your Prometheus server and necessary debugging machines should be able to reach them. Restrict access to Grafana server. Grafana, default port 3000, should also be behind a firewall. Public exposure, if necessary. If Grafana needs to be accessible from outside your internal network, always place it behind a reverse proxy, like Nginx or Apache, that handles SSL TLS termination, authentication, and potentially WAF, web application firewall protection. 2. Authentication and authorization. Grafana, change default credentials. As emphasized in Chapter 5, immediately change the default admin password. User management. Use Grafana's built-in user management to create different users with appropriate roles: viewer, editor, admin. Avoid giving everyone admin privileges. Integrate with central auth. For production environments, integrate Grafana with your organization's central authentication system like OAuth, LDAP, or Active Directory. This provides single sign-on (SSO), centralized user management, and stronger security policies, e.g., password complexity (MFA). Prometheus, no built-in authentication. Prometheus's web UI and API do not have built-in authentication. Solution: if you expose Prometheus over a network, always put it behind a reverse proxy, Nginx, Apache, Envoy, or a corporate API gateway that handles HTTP basic authentication, client certificates, or integration with an OAuth SAML provider. Traffic from your Grafana server to Prometheus can often stay on an internal, trusted network without authentication. 3. Secure communication, TLS SSL. Encrypt traffic. Wherever possible, enable TLS SSL, HTTPS, for communication between clients, your browser, and Grafana, and potentially between Prometheus and your exporters, though less common due to complexity and performance overhead for internal traffic. Grafana. You can configure Grafana to use HTTPS directly in its Grafana.ini configuration, but it's more common and recommended to use a reverse proxy for TLS termination, as discussed earlier. Prometheus exporters. Most exporters don't support TLS out of the box. If you scrape across untrusted networks, consider using a secure tunnel, VPN, or a proxy like Prometheus proxy. 4. Principle of least privilege. Dedicated users. Run Prometheus, Alert Manager, and all exporters under dedicated unprivileged system users, e.g. Prometheus Node Exporter. Never run them as root. Restricted file permissions. Ensure their configuration files, data directories, and binaries have appropriate file system permissions, readable only by the dedicated user and root. 5. Configuration best practices. Sensitive information. Avoid hard-coding sensitive information, like API keys or passwords for notification channels, directly in Alert Manager RML or Grafana.ini. Use environment variables or secret management solutions where possible. Service discovery credentials. If using service discovery mechanisms, e.g., AWS EC2, Kubernetes that require credentials, ensure these are managed securely, e.g., IAM roles for EC2 instances, Kubernetes secrets. Performance considerations for Prometheus. As your infrastructure grows, so does the amount of metric data. Managing this efficiently is critical for Prometheus's stability and your query performance. 1. Understanding cardinality. What is cardinality? In Prometheus, cardinality refers to the number of unique time series. Each unique combination of a metric name and its labels creates a new time series. High cardinality means a very large number of unique time series. Example of high cardinality. A metric HTTP request total with userid as a label if you have millions of unique users. Or a requested or sessionid label. Why is high cardinality bad? It directly impacts Prometheus's performance and resource consumption. Increased storage. More time series means more disk space required. Increased CPU memory. Prometheus needs more CPU and memory to store, index, and query a large number of time series. Slower queries. Queries over high cardinality metrics are significantly slower. Mitigation strategies. Avoid unique labels. Never use highly unique fields like userid, sessionid, requested, timestamp as a label directly as labels. These belong in logs or traces, not metrics. Aggregate data. If you need to count something unique, e.g., unique users, aggregate it before sending it to Prometheus, e.g., count unique users per minute-hour in your application and expose that aggregate. Relabeling to drop rewrite. Use metric relabel configs to drop high cardinality labels or rewrite them into lower cardinality values, e.g., convert URL product id 12345 to URL product id. Analyze status page. Prometheus's status TSDB status page and Grafana's Prometheus TSDB status dashboard can help identify high cardinality metrics. 2. Scrape interval and target count. Scrapping interval, the frequency at which Prometheus scrapes targets. Shorter intervals, e.g., fives, mean higher resolution, but also more data points and more load on Prometheus and the scraped targets. Longer intervals, e.g., 60s, reduce load but might miss transient issues. Balance. Choose an interval appropriate for the criticality and volatility of the metrics. For critical, fast-changing metrics, 5s or 10s might be appropriate. For static configuration exporters, 60s might be fine. Target count. The total number of unique endpoints Prometheus is scraping. Thousands of targets at short scrape intervals can strain Prometheus. 3. Resource allocation for Prometheus. CPU and RAM. Prometheus is relatively CPU and memory intensive, especially during query evaluation and data ingestion. Ensure your Prometheus server has sufficient resources. Monitor its own bytes, gagoroutines, and process total to understand its resource usage. Disk I/O. The Prometheus TSDB is designed for efficient disk writes, but it still requires fast disk I/O, particularly during compaction. Use SSDs for optimal performance. Storage configuration. Storage TSDB retention time. Configure how long Prometheus retains data. Default is 15 days. For longer retention, use remote storage solutions like Thanos or Cortex, as discussed in Chapter 8. Storage TSDB path, dedicated fast disk is recommended. 4. Query optimization. Recording rules. As covered in Chapter 8, precompute expensive or frequently used queries as recording rules. This offloads the computation from query time to scrape time. Label selectors. Be as specific as possible with your label selectors. HTTP request total job equals myapp, is more efficient than HTTP requests total. Time ranges. Avoid excessively long query ranges in Grafana panels, especially for high-resolution data that might be downsampled. Prometheus will fetch all raw samples within the range by default. Sum, by versus sum. Always use sum, by, to aggregate metrics that have many labels you don't need, reducing the number of time series processed at the query level. Browser caching. Grafana heavily uses browser caching. Optimize queries to be within a reasonable refresh interval. Performance considerations for Grafana. Grafana's performance is largely dependent on the speed of its data sources and the complexity of the dashboards. 1. Dashboard complexity. Number of panels. Too many panels on a single dashboard can slow down rendering. Aim for focused dashboards. Number of queries per panel. A single panel with many complex queries will load slower. Variables. Dashboards with many query variables or query variables that are slow to execute can significantly delay dashboard loading. Optimize these queries. 2. Data source latency. Prometheus performance. If Prometheus is slow to respond to queries, Grafana will be slow. Optimize Prometheus as described above. Network latency. Ensure good network connectivity between your Grafana server and its data sources. 3. Grafana server resources. CPU and RAM. While less demanding than Prometheus, Grafana still needs adequate CPU and RAM, especially for many concurrent users or complex dashboards. Database backend. Grafana uses SQLite by default for its internal database. For production, especially with many users or dashboards, consider configuring it to use a more robust external database like PostgreSQL or MySQL. 4. Browser performance. Complex visualizations. Some visualizations, e.g., highly detailed graphs with many series or very large tables, can be resource-intensive for the user's web browser. Browser caching. Ensure HTTP caching is configured correctly for static assets served by Grafana or its reverse proxy. Conclusion. Continuous improvement. Both security and performance are not one-time tasks. They are continuous processes. Regularly review your Prometheus and Grafana configurations, audit access, monitor their own performance metrics, and stay updated with the latest releases and best practices. As your infrastructure scales and evolves, so too should your monitoring strategy, ensuring it remains secure, efficient, and reliable. With these considerations in mind, your Prometheus and Grafana deployment will not only provide invaluable insights, but also serve as a robust and trustworthy component of your overall system.